The Internet Address Architecture. This chapter deals with the structure of network layer addresses used in the Internet, also known as IP addresses. We discuss how addresses are allocated and assigned to devices on the Internet. So in this chapter, we will discuss specifically the layer part, or the network layer part, how addresses are being assigned to devices via internet. So usually this is allocated by IANA, which we will discuss later. So basically that's the internet allocator based in US that provides this that's that provide a connection to Asia, US, etc. We also discussed the way hierarchy in address assignment aids routing, scalability, and use of special purpose addresses including broadcast, multicast, and anycast addresses, and how the structure of IPv4 and IPv6 addresses differ. So the hierarchy, which starts from allocating from IENA from a global address to regional address such as RIR to your ISP provider like PLDT Globe. Every device connected to the internet has at least one IP address. Devices used in private networks based on the TCP or IP protocols also require IP addresses. So every device needs at least one IP address, but in normal user contexts, it actually being handled by your router. So your router is being provided a one unicast address, and that unicast address are being shared among, let's say, 8 devices via DHCP, and it's stored the table in NAT, which we're gonna discuss in the future videos. Even the private networks that use this TCP or IP protocols, which we discussed in the previous video, also require that IP address. So it can use a router to that use DHP to share the connection, but it still need that unicast address. In either case, the forwarding procedures implemented by IP routers, see chapter 5, use IP addresses to identify where traffic is going. So the routing procedures, which we're gonna discuss in the chapter 5, which on the next videos, actually discuss how we route this. So we will gonna relax the assumption a little bit, just like what we did with operating system. So here it's gonna use that IP address to whether it's share it or to send it. Again, there's a source and target destination address for that to identify where the traffic is going. IP addresses also indicate where traffic has come from. IP addresses are similar in some way to telephone numbers, but whereas telephone numbers are often known and used directly by end users, IP addresses are often shielded from a user's view by the Internet's DNS. See chapter 11 for that, which allows the users to use name instead of numbers. So every server on the internet or every site that you go to needs to have an IP address, but it's being abstracted by DNS, which we also uh, talk a little bit in the previous video. Users are confronted with manipulating IP addresses when they are required to set up networks themselves, or when the DNS has failed for some reason. So if your DNS has failed, this is where you must configure your IP address itself. But it's being abstracted now by your router, so you need to connect to it via name on your Wi-Fi, because IP providers learn their lesson, and we will discuss that further. Also, it's one of their design principle that it is easy for users to connect to it, right? Like just like what we discussed in the design in the previous video. To understand how the internet identifier identifies hosts and routers and delivers traffic between them, we must understand the role of IP addresses, particularly in their administration, structure, and uses. So how do we actually administer what how do we configure that? What's the structure of IP address? What's its syntax that we need to understand to be able to use that? So to be able to understand how the internet identify each host and routers over this complex interconnected network. When devices are attached to the global internet, they are assigned addresses that must be coordinated so as to not duplicate other addresses in use on the network. So that's where IANA comes, and the RIR and your ISP provider. So for private networks, the IP addresses being used must be coordinated to avoid similar overlaps with the private networks. Groups of IP addresses are allocated to users and organizations. The recipients of the allocated addresses then assign addresses to devices, usually according to some network numbering plan. So, groups of IP address are allocated to organizations, and that organization then allocate addresses, then assign that addresses to devices, usually using numbering plan. For global internet addresses, a hierarchical system of administrative entities helps in allocating addresses to users and service providers. So again, for global internet addresses, a hierarchical system of administrative entities help helps in allocating addresses to users and service providers. So that's where IANA comes from, and then it routes it to RIR, which is your regional, and then to ISPs. Individual users typically receive address allocations from internet service providers that provide both the addresses and the promise of routing traffic in exchange for a fee. So to be able to route a traffic, you need to pay an internet provider. Later we will discuss how do we actually how to actually internet provider route your traffic from your laptop to the internet. Expressing IP addresses. Such addresses are often represented in a so-called dotted decimal notation. For example, 165.195.130.107. So this is an example of IPv4 address provided by your ISP. The dotted quad notation consists of 4 decimal numbers separated by periods. So a dotted quad notation means a decimal number 4 decimal numbers separated by periods. Each such number is a non-negative integer in the range 0, to 255 and represents 1/4 of the entire IP address. So each number in this 4 decimal numbers or 4 chop number or that dotted quad should be less than 255 and it should be non-negative. So the dotted quad notation is simply a way of writing the whole IPv4 address, a 32-bit non-negative integer used throughout the internet system using conventional decimal numbers. So it's simply simplifying the 32-bit non-negative integer that is being used to identify dot in the whole internet system using convenient decimal numbers. In many circumstances, we will be concerned with the binary structure of the address. Like Table 2.1 gives a few examples of IPv4 addresses and their corresponding binary representation. To get started, so here dotted quad representation 0.0.0.0. Here's the binary representation. As you can see, it's a 32-bit non-negative integer. 1 2 3 4 1, and then you have 1 on the second, and then 2 ones on 3. So this is how it's represented in binary representation. In IPv6, addresses are 128 bits in length, 4 times larger than one IPv4 addresses, and generally speaking are less familiar to most users. So it's times 4, 128 bits, so times 4 of this. The conventional notation adopted for IPv6 addresses is a series of 4 hexadecimal, hex or base 16 numbers called blocks or fields separated by colons. So it's still separated by colons, but instead of decimal, it's hexadecimal or hex or base 16. So that's the conventional notation. It's not a dotted quad notation, but it's a hex. An example of IPv6 address containing 8 blocks would be written as 5F05 colon 2000 colon 80 AD colon 5800 colon 0058 colon 0800 colon 2023 colon 1D small d 71. Although not as familiar to users as decimal numbers, hexadecimal numbers make the task of converting to binary somewhat simpler, because again it's a 128-bit non-negative number. So in addition, a number of agreed upon simplifications have been standardized for expressing IPv6 address. So first, leading zeros of a block need not be written. In the preceding example, the address could have been written as 5F05 2000. So as you can see, we the 0058 has been omitted, the leading zero in this 58. and the leading 0 of 0800 has been omitted as well. Blocks of all zeros can be omitted and replaced by the notation. So a block of all zero can be omitted and just be replaced by this notation, two colon. For example, the IPv6 address 00001 can be written more compactly as :1. Similarly, the address 2001 colon 0 db8 colon 0 colon 0 colon 0 colon 0 colon 0 colon 2 can be written more compactly as 2001 colon db8 colon 2, since those are combination of 0. To avoid ambiguities, the double colon notation may be used only once in an IPv6 address. So to avoid the ambiguity or the complexity of an already complex 128 bits, you can only use the double colon once to represent it. Embedded IPv4 addresses represented in the IPv6 format can use a form of hybrid notation in which the block immediately preceding the IPv4 portion of the address has the value FFF, and the remaining part of the address is formatted using dotted quad. For example, the IPv6 address FFFF 10.0.0.1 represents the IPv4 address 10.0.0.1. This is called an IPv4 map IPv6 address. So the reason why it is called IPv4 map IPv6 address is because the embedded IPv4 addresses represented inside this IPv6 format. So this is used for communication that supports IPv4 and IPv6. So let's say you want to use the IPv4, you're gonna use this 10.0.0.1. For IPv6, you're gonna use this double colon FFF, including that. So another another rule is a conventional notation is adopted in which the lower 32 bits of the IPv6 address can be written using dotted quad notation. The IPv6 address 0102 colon F001 is therefore equivalent to the address colon 1.2.240.1. This is called an IPv4 compatible IPv6 address. Note that IPv4 compatible address are not the same as IPv4 map address. They are compatible only in the sense that they can be written down or manipulated by software in a way similar to IPv4 address. So this type of addressing was originally required for transitions plans between IPv4 and IPv6, but is now no longer required. So what this means is that in 90s, since it's early in transitioning to IPv6, engineer think of a way to be able to use that IPv4 connection if there is an IPv6 on other network stock of the let's say host B. So these are the example. Let's just so here you see a host A has an IPv4 stock and IPv6 stock. Now what this will do is this stock will use this IPv4 link to IPv4 link the IPv4 link to connect to network IPv4 stack of N host B, but it wraps after that it will decapsulate that to IPv6 to make it compatible. They are not really mapped, so uh, there is some way that they make it possible to decapsulate it to be able to use that IPv4 path. So that's the key, the IPv4 path. In map, IPv4 map, IPv6, they actually, if your network support IPv6, they're gonna use IPv6 path. But in this compatible, they're gonna use an IPv4 link. So how it behaves, if both host and the network in between support IPv6, communication happens over the IPv6 path. Like packets carry IPv6 headers, routers forward using IPv6 routing table. If only IPv4 connectivity exists, the connection happens over the IPv4 path. So both paths can coexist in parallel depending on which protocol each application or destination prefer. So this is called a dual stack operation. So that's what we mean by 3 and 4, because we assume that it's either a dual stack, both end host A and host B has a dual stack, but incompatible, it only has one path, which is the IPv4 path. So here, notice that ARP is placed by NDP, Neighbor Discovery Protocol, under IPv6. So the dual stack host maintains both mapping mechanism. So these are the TCP IP layer. This is where they go in the TCP stack, TCP or IP stack. So IPv4 in the network layer, and the ICMP or IPsec are the one controlling that before multiplexing or demultiplexing. Let's say you're trying to multiplex, sending it from A to B, you're gonna start with an IPv4. So instead of 3.5 first here, you start with the network first. You create the packet, and then you control that packet, whether making it more secure by adding it using IPsec, or controlling it using ICMP before transferring it to link adjunct, which is where the ARP. So the link adjunct is where your Wi-Fi, the Ethernet, where it actually connects to the internet. So it connects to the internet, right, via converting or multiplexing this IP address and the MAC address of your interface, and then sending the packet via signal to your router or Wi-Fi, and then sending it to the internet. So here, IPv4 and IPv6 coexist in layer 3 network, two parallel stacks inside the network layer. ICMP-v4 and ICMP-v6 layer 3.5 ANJAC support protocols aligned with their respective IPv version. Another key difference here is that the ICMP or the adjunct, they are dependent on the layer 3, which is the network. So for V4, you have ICMP v4. For V6, you have ICMP v6. Layer 2.5 adjunct ARP used with IPv4 and DP with IPv6. So these are the adjunct. Now these are the above. Works identically regardless of a IP version. So these are abstracted. It doesn't care about this bottom layer, whether it's IPv4 or IPv6. So the TCP or UDP protocol you use on your application doesn't really recognize the difference with that, and that's what makes it work. That's what makes it amazing. The layer 3 and below are handled by your ISP provider, and the layer 3.5 and below are handled by your ISP provider. The 3 and below 2.5 is handled by your ISP provider. 3.5 to 7 is handled by your application. So the network layer 3 does the main job. It does the routing, the logical addressing, the IPv4 and IPv6. So that's your ISP providing, or your router providing a unicast address to you, forwarding packets between networks. That's where also it forward packets. It knows where next router it should route to, and it does that in a lightning speed because this ISP provider are connected to this undersea cable that has a lightning speed connected to the internet via BGP, which we're gonna discuss later. But the network adjunct 3.5 layer is made of support protocols that depend on the IP layer to work. So this network adjunct, the reason why they're adjunct is because the IP layers start first. They are dependent on that IP network. Before that, without that IP or unicast address provided by your router, it will not be able to configure that because there's no packet to begin with to send it to the internet to. They're not replacement for IP, but rather helpers that sit conceptually above it. Examples: ICMP-v4, ICMP-v6 use IP headers to send control messages like destination unreachable. So this ICMP, this is actually how it works. It uses the IP headers to send a control messages. So it like provide the error, like the destination. Let's say you're trying to demultiplex from nhost B to nhost A. It will be able to read that IP header once it gets to that 3.5 layer, and if it's destination unreachable, it can immediately dismiss that. IPsec, it encapsulates or secures IP packets. So this is where when you can configure the nhost A program in its network adjunct IPsec, you can encapsulate the IP packets created by your network layer, whether it's IPv4 or IPv6. IGMP manage multicast group membership over IP. So this is where you chose to activate the multicast, whether it needs by your app, like for Zoom, or like calls between multiple people for video call. If you're creating a video call app, you need this capability. You need to activate that. That's where the configuration come, but by default it is not activated. So while ICMP messages help IP, they're actually encapsulated inside IP packets. So the ICMP, which is the with use the IP headers to send control messages, are actually encapsulated inside the IP packets. So it's kind of like an additional layer to be sent. It's kind of like the header and trailer we discussed in the previous video, meaning they ride on top of IP, not below it. So here are the simple terms. 3. Use IPS transform above IP. IPv4, IPv6 provides addressing and routing below adjunct. So the diagram intentionally shows network adjunct above network because adjunct protocols depend on IP to carry them. So again, IP first before the network adjunct. Without IP, you won't be able to create it. So step by step, when host A sends data to host B, so this we explain how the compatible the IPv4 compatible IPv6 actually convert that or use the IPv4 FAT and then later decapsulate the packet into IPv6. But again, this is no longer used. It's just a great innovation that time to be able to use that if you don't have an IPv6 path, but that's not being used. But let's see how it works when sending from host A to host B. Application and transport layers. Host A application like HTTP over TCP produce data. two transport layer TCP or UDP segments. The TCP or UDP transport layer segments it and adds header. It passes the segment down to the network layer. So it's the IP first, which is the IPv4 or IPv6. Now in network layer IPv4 IPv6, at this point, host A builds an IP packet. So it adds a source and destination IP addresses. So this is where your router does all this work, right? It provides you the unicast address, or it separate or share the DHCP. It provides you this unicast address to your router. So it builds a source and destination IP address. So it puts the destination IP address inside the packet that you want to send to the network or all over the internet. And then it calculates checksums, the errors that may be included here, the TTL, time to leave, etc. So this is being done in the network layer, because this checksum, depending on how you can figure the TCP segments or the TCP layer with your application, you can configure the errors you will record. The time to leave is the time to leave of this data before it disregards it on the network. That's why whenever you're sending something, sometimes your time to leave is so fast that it didn't reach the destination. That's where the network issue comes. Now network layer IPv4 or IPv6, at this point, host A builds an IP packets, right? So this is the main data packet. Now network adjunct layer 3.5, control and security helpers. Here's where the adjunct protocols come in, and each behaves differently. So the adjunct protocol ICMP v4 or v6, so when it appears, it's sent beside or after a packet. So you have a choice to configure this. It reports errors or diagnostics about IP delivery, like destination and unreachable. It does not modify or secure the original packet. Instead, it's a separate controlled message using IP as well. So the IP spawn this. Remember, the protocol object can be instantiated in TCP or IP protocol. The IP sec, however, wraps around the IP packet. So it wraps around because it's securing it. It secures the packet by adding authentication or encryption headers, effectively transforming the original IP packet into a protected one before it's handed down to the Ethernet or to the link layer. This is essentially how you encrypt your data. IGMP or MLD, periodically or on demand. It helps manage multicast group membership, network control. So this is essentially where, for video call app, whenever you're trying to request a call for multiple people, this is the network adjunct you use. So it happens periodically or on demand. So this is kind of like so you manage the IP basically on how it will be sent. It is not wrap around. You're basically instantiating multiple of this IP to be able to send to multiple target. So because you're trying to send multi to a group, so it's not beside like ICMP or after a packet. It doesn't wrap to ensure the encryption like IPsec, but periodically or on demand to be able to instantiate multiple of that to request to a target, multiple target. So ICMP equals to control after or alongside IP communication. IPsec equals modifies or encapsulate the IP packet for security. IGMP or MLD, a network management messages using IP. That's why we call this group the network adjunct layer. It's not always active, but it sits logically above or around, around layer 3 to manage, secure, or monitor what IP does. Again, this is how you, by default, this does not TCP or IP architecture does not support this advanced feature to be able to be flexible. If you need that, you need more configuration on your end, but based on the architecture, to be able to, I think it's fade sharing or end to end, you need to configure it yourself. This is the beauty of TCP or IP, and this is actually what makes TCP or IP useful over the internet, is because of this. You have this packet, you have a choice to secure it, or you can access your own network from your internet provider, and those internet provider provides you a data center that is secure, right? And they manage the routing, the packet, etc. This is what makes the internet secure, but it's not that secure in a sense that no um, possible vulnerabilities, because there's always that, but at least for most use cases, 99% of the time, it is secure. Now, link adjunct 2.5. Once the IP or IPsec packet is ready, it goes down to layer 2.5. So ARP for IPv4 or NDP for IPv6. So this step resolves the destination MAC address for the next hop. So basically, this layer try to, since you have the target address or MAC address of the network interface device that you want to send data to, this is where you resolve that. It's necessary so the data link layer like Ethernet or Wi-Fi can actually deliver it over the physical medium. Let's say you're sending data to an actual phone, right? This like you're message from your phone to your mother's phone. So this is where your mother's phone are actually network interface of your mother's phone, for example, to other country is actually stored. Now data link plus physical layer, finally the full built frame with MAC header plus encapsulated IP or IPsec packet is transmitted to host B. Now here, summary of the logical order. What happens in stage 4, app creates data, HTTP or DNS. And then transport segments it, TCP or UDP. And then IP builds packet, IPv4, IPv6. Then adjunct secures or manages or reports, which is IPsec wraps, ICMP reports, IGMP manages, whether it's for multiple groups or a unicast, just one IP address. Link adjunct resolve addresses, ARP or NDP for IPv6. So they resolve MAC, which is the unique identifier of the network interface of the device you're trying to send to. Frame sent physically via Ethernet or Wi-Fi. So yes, you're right. The adjunct protocols can control, secure, or report on the packets that IP creates before or around the encapsulation to the link layer. So here, now let's go back to IPv6. So we see the full picture on how this IP address actually work. Now let's discuss the history on how we design these IP addresses to be provided to different ISP or to different devices across your routers on your Wi-Fi. Now, these are the examples of IPv6 addresses and their binary representations. So for this, hex notation, 5F05 colon 2000 colon 80 AD colon 5800 colon 58 colon 800 colon 2023 colon 1D71. These are the binary representation. So here for colon 1, so you see you only have 1 at the end of this 128 bits. For this colon 1.2.240.1 or colon 102 colon F001. You only have 1 at the 1, 2, 3, 4, 5, 6, 7 at the 7 and 8 of this hex binary representation. So in some circumstances, when expressing a URL containing an address, the colon delimiter in an IPv6 address may be confused with another separator, such as the colon used between an IP address and a port number. In such circumstances, bracket characters, open and close bracket, are used to surround the IPv6 address. For example, the URL http open square bracket 2001:0db8:0583:08d3:1319:8 small a2e 0370:7344 closing square bracket 443 refers to port number 443 on IPv6 host. So basically, you use this IPv6 address in port number 443. Let me check what is that port number 443. Oh, so it's for TCP port for HTTPS. So it's an encrypted version of HTTP. So that's how you use the IP and convert it in modern browser to be able to connect to that IP address, or to if you don't have the need to be able to get their files online, or through their to connect to their application, because it's an end host as well. It has their program. So their program, since you're, for example, in end host A, where's that? Here in this graph, let's say you're end host A. So here, let's say your IPv6, you're able to connect to that network layer. It converts to that transfer. Now you're on their application. So in their application, they may provide the interface. For example, for front end, the React, right? And there could be have multiple pages. And that multiple pages, when you click something on it on the front end, it will then connect to the back end, or in their back end, such as it could be a TypeScript if they're using Firebase or Firestore, or it could be just a MongoDB for database. So those will trigger almost instantaneously, because once you access the app, there's this called server-side rendering that allows them to serve you the entire app in one go. So essentially, all the front end are there, and then you just need to click something on it, and then once you click, that will eventually trigger a connection again from your front end to the back end, and their back end is open, or open that interface. So that's another application, or end host, and then provide you the function or data that you want, and then based on that, it will be read by your front end again. So depending on data or output they get, will be shown to your screen. So that's essentially the read, write, and modify framework on how computer actually works, based on inside the machine book. Basically, you essentially reading, writing, or you have an input, you have a process, and then output, and the output is based on the new data that you create. And that's what makes this computer amazing, by the way. That's what makes it different from calculator, because they allow to store the previous data and allows you to act based on that data, previous data, or to choose to manipulate or create a completely new data based on your input. So as you can see now, the calculation output is not the numbers, it's actually a pixel that you shown on your screen. So by the way, let's go back. So here, 2001:0db8 7344 using the HTTP or TCP in IPv6 protocol. The colon 7344 is actually a simple HTTP. So the flexibility provided by RF C4291 resulted in unnecessary confusion due to the ability to represent the same IPv6 address in multiple ways. So remember, we convert this to an IPv4 path using the last bits. So because of that, there was a confusion. So to remedy this confusion, RC 5952 imposes some rules to narrow the range of options while remaining compatible with RFC 4291. They are as follows. Now, they make it simpler. Leading 0 must be suppressed, like 2001, so it's still the same with before. The colon construct must be used to its maximum possible effect. So most zeros suppressed, but not for only 16-bit blocks. So it's not only for one time, not only for 16 blocks. So if multiple blocks contain equal length runs of zeros, the first is replaced with colon. So you can now use this colon construct to its maximum possible effect. So the hexadecimal digits through F should be represented in lowercase. So the hexadecimal decimal digits A through F should be represented in lowercase to make it simple. Now the basic IP address structure. IPv4 has 4,294,967,296,000 possible addresses in its address space, and IPv6 has 340, I think it's trillion, let me see. I think I cannot, it's basically infinite, right? So because of the large number of addresses, especially for IPv6, it's convenient to divide the address space into chunks. So the reason it's that high is because it's 128 bits. It's 4 times, compounding compared to IPv4. So here, what it means to have an IP address. So when you connect any device, so let's to be able to understand these abstract addresses and how it is being provided from IANA Global Internet down to your laptop or to your router, we must need to understand how your laptop used this unique IP address before we discuss the history on how it actually allocated or what are the design that was thought of when creating or designing this IP address, because this is actually discussed as well in cloud whenever you're trying to subnet an address for your private network. So this is so useful whenever you're creating a full stack application. So what it means to have an IP address: when you connect any device like laptop, phone, etc. to a network like Wi-Fi, mobile data, etc., your network layer 3, assigns your device an IP address. That address says, this is who I am in this network right now. There are two kinds of addresses you can get. Private IP, example 192.168.1.5. Who gives it? Your Wi-Fi router. What it means, used inside your home network only. A public IP, 203.0.113.42. Who gives it? Your ISP or internet provider. It's used on the internet so that websites can reach you. This is actually how website also track your location. It determines your public IP of your router, and because the PLDT or the internet knows that it is from PLDT, therefore it knows you. So when you discover when you disconnect and reconnect to Wi-Fi or laptop case, let's say you're on your laptop using Wi-Fi at home. Inside your home network, your router runs a service called DHCP, Dynamic Host Configuration Protocol. It lists you an IP address like 192.168.1.7 for a certain time, like 24 hours. If you disconnect and reconnect quickly, your router usually gives you the same IP again, because that router has a program in it. It is configured that if you're disconnected within a certain time and then went back to it at this it's still within the time frame, it will provide you the same IP. So if you stay offline for a while or the router restarts, it might give you a different private IP like 192.168.1.9. So on the internet side, your router itself has a public IP 203.0.113.7. It doesn't change. That's the unicast address. So basically, your router only provides one unicast address. Later we will discuss why. That's what website actually see. Your ISP may keep it the same for days or weeks if they use sticky DHCP, or change it each time your router reconnects to them. So even if your laptop's private IP changes, the world may still see the same public IP as long as your router keeps it. Now in mobile data, it's a little bit different. When you turn on mobile data, your phone connects. So before we go into this, the reason why you only have one unicast address each router is because a router IPv4 is a limited address. Unless you're using IPv6, for IPv6 you may have like millions or even more than that. Basically, it's a huge addresses provided to you by your IP, because there's a lot of available addresses for that. But for IPv4, there's enough device in the world to be able to consume that. Remember, it's only a billion, and there's like more than billions devices around the world. So on your mobile phone or mobile data, when you turn on mobile data, your phone connects to your carrier's network. The carrier system gives you a phone public IP, often IPv6 now, sometimes IPv4 too. When you turn data off, that IP is released. When you turn data back on, the carrier usually gives you a different IP, unless you reconnect within a very short time. So here the change is more often. Also because a mobile data switches or borrow networks in case the provider like Smart does not have connection on that area to Globe. So it definitely changed there. But they often change basically more than router or Wi-Fi. If you think about that, that makes sense, because usually if you're using mobile data, you're somewhere outside of your home. But when you're using router, you're inside your home, right? So here, so yes, you often get a new IP every time you toggle data or move to a different cell tower region. But the carrier may also use NOT. So this is also why it's important to buy like these latest gadgets sometimes. I mean, not that advanced, but because they have this better translation of network. So let's say it's really important for you to have data using your device. It's important to have that latest or enough technology, not the very old one. So yes, but the carrier may also use NAT, network address translation, meaning thousands of phones share one public IPv4 and get unique private addresses internally. But that's not common. But it also possible sometimes, depending on the complexity of the network area there. So do you get a new IP each time? Laptop reconnects to same Wi-Fi quickly? Usually same. Public or private IP changes? No, usually same. Public IP changes? Usually same. Why? DHCP list not expired. So because of the DHCP algorithm, inside your router. Laptop reconnects after hours or router likely. For private IP changes, public IP changes maybe. Why? New DHCP leases or new ISP assignment. Phone targets mobile data. Private IP changes, yes. Public IP changes, usually yes. So there's a private and public IP address as well in mobile data. Why? New connection to carrier. Could phone stays on mobile data. Private IP changes, no, because it's the same. Public IP changes, usually same, because it's stay unless you move around. The same session maintained because you're having the same session again. With another thing is that whenever you're trying to send, for example, one message from, let's say, Philippines to Japan, whenever the receiver send back message to you, they send back using that session. Let's say they do that in the internet, okay? Not through networks or normal messages. Let's say you send via Wi-Fi or networks. They will maintain that connection and then send a message to you or reply back using that session, which makes it fast as well. And it's the same principle with this. If the phone stays on mobile data. Now, public Wi-Fi like coffee shop, private IP changes, yes. Public IP changes, yes as well. Why? New network and new NAT. So yes. So a public Wi-Fi, of course, you're connecting to a different Wi-Fi. Therefore, your IP changes. That's why when the website tracks you there, they're gonna see the Wi-Fi of your coffee shop instead of your router at home. So yes, IPs can and do change, but how often depends on your connection type, Wi-Fi versus mobile, how your ISP routes manages the HCP leases, whether you stay connected continuously. So why that matters, tying it to your network layer. So in your TCP or IP terms, your network layer, IPv4, IPv6 addresses can change depending on which network your device joins. Your transport layer, your network layer, IPv4, IPv6 address can change depending on which network your device joins. So as you can see, whether you're in a coffee shop or on a different location, your IP address changes. And that's how website tracks your location, depending on which your network device joins. Your transport layer, TCP or UDP, depends on that address for sessions. So the sessions that I mentioned earlier, the TCP or UDP transport layer of your program you're using on your device session to connect to the internet depends on that IP. So if your IP changes, active connection on that TCP or UDP in transport or on your application will also change, or it will break. That's why downloads can stop if your Wi-Fi switches to mobile. So your app could crash if you change your location using mobile data. It's not your hardware that changes, it's the network layer identity your system is using that moment. But again, it's abstracted from the application, which makes it scalable, or the concept of fate sharing or end-to-end. I think that's the end-to-end concept, but doesn't matter. But the scalability and the flexibility is the principles there. So IP address are grouped by type and size. Most of the IPv4 addresses chunks are eventually subdivided down to a single address and used to identify a single network interface of a computer attached to the internet. So that's where your router unicast address come, or to some private intranet if you're using a company IP. So it's grouped by type and its sizes. Most of the IPv4 addresses chunks are eventually subdivided down to a single address or unicast. These addresses are called unicast addresses. Most of the IPv4 address space is unicast address space, which we will gonna later or in the future video we will gonna discuss the different types. And most of IPv4 really is a unicast address, which is a great knowledge to learn. So most of the IPv6 address space is not currently being used because it's a lot. Beyond unicast addresses, other types of addresses include broadcast, multicast, and anycast, which may refer to more than one network interface. So basically, this is just a network interface you use to connect to the internet. And basically, you need an internet provider that connects or that serve that traffic to be able to connect. That's why you have a mobile data plan and you have this internet plan. So before we classify this or we start with the history, let's start with the classic multicast separation of IPv4, sorry, classic unicast address such as class A, class B, class C, and then all the way down to multicast broadcast address. We need to understand at a higher level how do you become an ISP provider, because I think that's what's missing. That's the abstraction that people, including myself, wants to know to really get down to the detail. So how do you actually allocate these IP addresses? Again, it starts with IANA, which is the global blocks. So to request that, you usually need to prove a need that there's a lot of user that wants to connect, and they will allocate that. And then every time you connect to the internet, which is the BGP, it tells the internet that you are from Philippines or PLDT, depending on your ISP provider. So they do that, of course, to verify your identity. They don't want someone coming from unknown places to be able to access their data or to connect with them, right? So you need to prove a need, you need to prove your integrity as a company, etc. Now, how those chunks reach you personally? When you connect to the internet, your ISP, internet service provider, or mobile carrier owns a chunk of that global address space. Example, they might own 203.0.113.0/24 in IPv4. When you connect, they dynamically assign one of the addresses in that chunk to you. So they use an algorithm, kind of like the DHCP. Example, your device might get 203.0.113.7. If you disconnect and reconnect, you might get another address from that same chunk, 203.0.113.8 or .10. So the chunks are the blocks of addresses your ISP or router manages and distributes temporarily to you using DHCP or IPv6 configuration. So depending on how you connect, where you connect, it's a dynamic provided by your ISP. So group by type, unicast, broadcast, multicast, and anycast. So when you use the internet on your laptop or phone, you're almost always using unicast address. So address type unicast, who is it for? 1-to-1. Example, 203.0.113.7. Used by you, yes, your unique address. Broadcast, 1-to-all, IPv4 only, 255.255.255.255. It is used inside LAN, not across internet. Multicast, 1-to-many, 224.0.0.1 for IPv4, FF00::1 for IPv6. So that's the example. Used by some apps, including streaming or routing, because you're sending like different connection to different, kind of like one-to-many video call. Anycast, 1-to-1 of many, closest node, often used in IPv6 like DNS resolvers. So it is used not directly by you. Usually it is used by some other by providers, such as for DNS resolver, to be able to route you to that name or in the internet. So when your laptop or phone gets an IP, it's always a unicast address. One IP for one interface. That's the most IPv4 address space. That's the most of IPv4 is unicast pair means. So most of IPv6 address space is not currently used. So that's what we mean earlier that most of the IP address we use or being connected to, whether it's mobile data, is actually a unicast address. Whether it's from router or an IPv4 provided by a mobile uh, provider divided, uh, it's usually a unicast address. So for mobile, again, they usually change that whenever you reconnects. And for Wi-Fi, they share that using DHCP to be able to keep the IPv4 address maintainable. Now, what does the most of IPv6 address space is not currently used, meaning, which we discussed earlier. IPv6 has an astronomical huge address space, but only a tiny fraction is being used today. Why? Because we don't yet have many devices. ISPs and organizations only need to allocate small chunks, like /48, /64 blocks out of it. The rest is reserved for future growth. So even though IPv6 could give every grain of sand on Earth its own IP address, in reality, only a few big chunks have been assigned and subdivided so far. So connecting it to your everyday experience. So let's ground it in you again. Situation, you connect your laptop to Wi-Fi. What happens? Router assigns a private unicast address from its chunk, like 192.168.1.0/24. So again, sorry, when you connect your laptop, use Wi-Fi router. So your router assigns you a private unicast address from its chunk, like 192.168.1.0/24. Connection to address chunks. So your router has a small chunk of private IPs it manages. So the router has its private IP that it manages. Usually it's just one unicast address. And it share it among 8 devices, for example, via DHCP. So another situation, router connects to ISP. ISP assigns the router a public unicast address from its chunk. So this is where the actual public unicast came from. So the private is actually the one being shared via DHCP, and the public unicast is actually what it shows to the internet or to the world from its chunk. So connection to address chunk, ISP owns a chunk of public IPv4 IPv6 addresses. When you turn on mobile data, carrier gives you a phone a public IPv6 and sometimes IPv4 address. And then connection to address chunk, the carrier owns large chunk on the IPv6 space. And hands them out dynamically. And so for mobile phones, since it's changing all the time, the IPv6 and IPv4 usually it's IPv6 for phone. Since there's a lot, the IP address allocated to you by mobile provider is also changing all the time. So when you disconnect, the address will return to the ISP's full, the chunk it came from, and then you may get a new one next time. So that's how it allocates using mobile data. So when an internet provider says it allows up to 8 devices, that doesn't mean the ISP is giving you 8 public unicast IP addresses. It usually means your router can handle 8 local devices through a process called network address translation. So this is what the DHP means. It provides you 8 private address using one unicast IP address. So what's actually happening? The ISP gives your router one public unicast IP. like 203.0.113.7. Inside your home, your router runs a DHCP server that gives each device a private IP. So it's kind of like sharing that, but connecting it using that one public IP address connected to the internet. So for example, laptop 192.168.1.2, phone 192.168.1.3, TV 192.168.1.4. When those devices access the internet, the router translates their private addresses into its single public IP. So again, when those devices access the internet, the router translates their private addresses into its single public IP. So this NAT using the NAT like divide the public IP, but the router then translate that into a public IP to connect to the internet. It tracks who sent what using port numbers in a NAT table. So the router tracks who sent what in its NAT table using port number. So that's what the NAT and the port number now are being used is to track the device that sent that packet. So 8 device is not equals to 8 public IPs. It means your router can share its one public IP among up to 8 private clients. So why ISPs don't give every device a public address for IPv4? Because there are only 4.3 billion IPv4 address total, and almost all are already allocated. If every phone, laptop, and TV gets its own IPv4 address, would run out instantly. So basically, what this means is that your ISP tried to minimize the use of their allocated IPv4 because they're paying for the data center and for the rental of the undersea cable for this. So they also ask you to get or to pay if you want more access for like higher gigabytes cable. So it's already there. They're connected to the internet, and they won't be creating this huge like undersea tunnel because it takes time first and it costs a lot. So they usually rent that to others as well, such as PLDT and NTT of Japan and other telecommunication provider. Invest in this using there are billions of dollars to be able to create this, and they just rent out some part of it to be able to access and connect to the internet. And basically what you just need to do is to connect to their underneath local cable and use they're just gonna use a router. If you say yeah, kind of like what router being used at home to be able to route you the traffic from the internet. It's already there. It's just a matter of speed and of course the troubleshooting that they have to go through to be able to install it to your Wi-Fi. So that's basically what you're paying. But if basically everything is free at that moment because they've already built the infrastructure. So here so NAT lets millions of customers share limited public IPv4 address. So that's one big reason IPv6 was created. It removes the need for NAT because its address space is so enormous. So that's the reason why this IPv6 is created, is because it removes the need for NAT in that router because it has a large address space. So how do they know what's free or used? So the way to know what's free or used, or to be able to troubleshoot this issue or access issue in this already existing internet, is using this IP address management IPAM database to track allocations on the IPs they allocate, whether it's to your router, etc. DHCP pools to issue addresses dynamically. So the DHCP is how they issue the address you connect to your Wi-Fi and to your phone for IPv6, NAT logs to map internal users to public addresses. So NAT logs is being used by the router to map the port number and the NAT. The port is actually the logs to translate, to track it, what device sent it using your Wi-Fi. Reduced to authenticate which customers get which IP. So these are the authentication. Without this authentication, you won't be able to access. So this is how they manage and route and troubleshoot this connection issue. So all of that ties back into billing, usage tracking, and abuse prevention. So BGP is actually what I'm saying. It's the internet glue. Yes, it's the key. So when you register or when you create your own internet provider, what you're basically needs to do is to be able what the basically allows you to do is, yes, they will allow you an access on the BGP border gateway protocol, which is the internet. It will allow you to connect to the internet and to route traffic to you, as long as you are a verified telecommunication company like PLDT. But there's a lot of steps to get into this. So basically, it's just one software configuration, and that's it. They will be able to connect you. So think of it like this: the internet is not a single network; it's a network of networks glued together by BGP. So when PLDT says I have 203.119.0.0/16, send me traffic, so it broadcasts that message through BGP routers. So this is where the broadcast addresses came from. So it broadcasts that message through BGP routers. So it used the BGP routers that provided by this regional internet provider to all its connected peers like Japan NNT, SoftBank, Singapore, Singtel, US Level 3, AT&T. So that's how it communicates there. So each BGP router keeps a routing table like a map of which AS number owns which IP range. So this big seemingly small or one routing table, which is the BGP routing table, actually keeps track of all the interconnected networks in the world, and that's what makes us this interconnected system works. So yes, BGP is the internet's routing brain. So basically, the regional RIR allows access to ISP provider using this. So when AppNIC allocates a block, what physically happens? So when AppNIC allocates an IP block to PLDT, this is the regional provider, no physical cable is delivered. Instead, AppNIC updates its public WhoIS database. So it's basically updating its database, like here, inetnum : 203.119.0.0 to 203.119.255.255, net name : PLDTnet, DSCR : PLDT dot comma Philippines, country : PH. So then PLDT configure its BGP edge router to announce that block. So PLDT is being provided, or they can buy their own this BGP edge router to announce its block that has been provided to them. So that's no new undersea cable. So they are not creating an undersea cable. Basically, they're allowing access or rent for that undersea cable, and they are configuring it via this BGP edge router, basically via software. The undersea cables already exist. PLDT is already physically connected to global carriers like NTT, Singtel, etc. So allocating IPs only gives them legal ownership and routing authority over those numbers. So it provides them legal ownership to make sure that they won't mess up or they won't do anything fraud. That's why there is you need to prove the need. So allocation is equals to logical permission, not a new physical link. Now this is the physical side of an ISP, the real machine. Now let's talk about its physical servers and routers behind all those abstract terms: IPAM, DHCP, NAT, etc. So the BGP routers devices, it came from Cisco, it could be came from Juniper, Huawei, Nokia routers. Hardware: multi-core, network CPUs. So it's a multi-core processor, but specialized to network CPUs. So it has CPUs as well. Multiple 100 gigs fiber ports. So it has like multiple 100 gigabytes fiber ports. Storage minimal, routing tables in RAM. So small RAM. OS, Cisco iOS, JuneOS, or Huawei VRP. So as you can see, there's a specialized company that handle the hardware and OS, particularly Cisco and Huawei. So you can see they have the OS and device. Purpose, it routes packets between ISPs. So you can buy this if you want to be an internet provider. They sit in data centers or internet exchange points like Fixed Philippine Internet Exchange. So this fixed or internet exchange point, usually it's near the sea or near the border. We actually have here in the Philippines in Camarines Norte, Batangas, etc. And those are being protected by bodyguards. So IPAM, what is IPAM? So the physical form, a Linux or Windows server running software like Infoblox, PHP IPAM, open source. So that's an offer. They're using an open source code. They could be using an open source code. And also this OS is actually an open source, a Linux storage database, MySQL, PostgreSQL. So my the internet provider actually use a MySQL to track the allocated IP address. Specs maybe 4 to 8 CPU cores. So 48 CPU cores. It's not an i7. 16 to 64 gig RAM only, and 500 gig SSD. So as you can see, even in this physical server, we still have RAM and SSD. Role, track which IPs are assigned, free or in use. And also they have a backup like this as well. They have a software that in case this got its hardware failure, they will be able to survive immediately. Kind of like in cloud. So example record in IPAM. So IP 203.119.1.12, owner, Fiverr user number 302, location Makati, status active. IP 203.119 .1.13, owner free, location Manila, status available. DHCP server. So it is somehow the same with the DHCP with your router. So it's running Linux like LSC DHCP _ server or Cisco iOS for enterprise. As you can see, the OS mostly for this are actually Linux and Cisco. The specs are modest, like 8 gig RAM only, 2 CPU cores, and 100 gig SSD. No purpose, hand out IPs to customer modems or routers. So it provides IPs to customer modems and routers for private addresses. So like these are the sample DHP configuration example. So subnet 203.119.1.0, netmask 255.255.255.0. Inside it, range 203.119.1.50, and then 203.119.1.250 semicolon. Then next line option routers 203.119.1.1 semicolon. Then next option DNS servers 8.8.8.8 semicolon. Next default dash list dash time 86400 semicolon, closing semi-curly bracket. So when your modern modem connects, it asks for an IP and this server responds, not gateways. So when your modem connects to the internet, it's asked for an IP and this modem actually responds to them. You know, it could be in Camarines Store, etc. Or depending on the where it's located. So not gateways. Hardware, specialized router or firewalls translate private IPs into public IPs. So the NAT gateways we discussed earlier, very high specs, very high throughput, 40 to 400 gigabytes per second, redundant CPU. So OS. So you notice the reason why they are fast is because they're using mostly specialized hardware designed for them. Like here, very high throughput 40, and OS often embedded. Cisco again, Cisco ASA, Juniper, Linux NetFilter. So they maintain NetLogs, etc. So it's an example of logs timestamp 10.0.5.12 colon 50234 203.119.1.8 colon 443 translated to 203.119.100.45 colon 50243. Radio server purpose authenticate customer session assign IPs. So these are they also assign IPs, but they can also authenticate first. Linux, it used Linux or FreeBSD with FreeRadius or Cisco ACS. Specs. The FreeRadius, I think we discussed this in the previous video with our Linux troubleshooting. Specs, light 4 to 8 gig RAM, then 200 gig disk. So it has 4 to 8 gig RAM and 200 gig disk. Example logs user colon fiber underscore 032 assign underscore IP colon 203.119.1.74 session underscore start colon 2025 10 then space 17 space 03 colon 4. They connect to billing system so that, for example, a 100 gig plan means bandwidth throttling or quota enforcement. So how ISP defines 8 devices or 100 gig plan? So how do they actually define an 8 devices and a 100 gig plan to your router? So these aren't about IP addresses, they're about service policies set in software only. So again, it's being managed by software. Plan type 8 device limit controlled by Wi-Fi router. Mechanism DHCP in that router limit only 8 leases allowed. 100 gig data cap. So radio/billing system, it is managed by that software or that hardware that has that software. It tracks traffic usage per session. So that's what they have authenticating if you go more than 100 gig allowance of your Wi-Fi. 50 Mbps speed. This managed by a specialized router. Cost, quality of service. Mechanism bandwidth shaping on port or interface. So it shaped the bandwidth on the port or interface to control the speed. So even if all 8 devices are one public IP, PLDT enforced limits through internal policy servers through IP allocations. So they use the servers on that, so how do you create those servers on your own? So how later we will discuss that as well. How ISP divides address blocks in routers. So let's say you got 203.119.0.0/16 from AppNIC. So you can subnet it manually in your router. So interface VLAN 100, next line IP address 203.119.1.1 and then 2.5.255.255.0. Next line interface VLAN 200. Next line IP address 203.109.2.1, 255.255.255.0. So that's how you divide it. Now VLAN 100 and VLAN 200 are separate networks. Sorry, that's how you separate networks. Each with 254 usable IP or 254 unique unicast address. To make them visible to the world, your edge router advertise both through BGP. So this BGP has a different kind of address, which is broadcast. It broadcast that to the world. That allows to other ISP in the world to connect to it. So who built the undersea cable? It's not AppNIC. It's built by private consortia, groups of telco. For example, APCN2 owned by PLDT, NTT, Singtel, Telecom Malaysia. Asia America Gateway, AAG, includes Globe, PLDT, AT&T, etc. They jointly fund and maintain the cable. So when you buy transit, you're paying for capacity over those cables, not just the right to use IPs. How much it costs to get IPs? When an ISP requests allocation, membership fee, AppNIC annual membership is 500 to 5,000 USD dollars. IP resource fee based on size, like /22 IPv4 equals to 1,200 per year. So as you can see, it's not the allocation of addresses is expensive. It's the renting of this actual cable. So undersea capacity separate hundreds of thousands to millions USD depending on speed, like 10 gig speed, 100 gig that you will pay to these service providers that funded this. So what physical management looks like inside data centers. So inside a carrier data center or internet exchange, they have racks of routers. So internet exchange, that's where the, near the sea in Camarines Norte, they have a racks of routers, thousands of fibrous cables. Technicians patch and label fibers, PLDT, ISP to new to 1 to port 1/0/1. Power systems, cooling, monitoring, access controlled by biometric security. So here we have a links ph-ixp/isp-new-1/port-1. We have a status up, bandwidth utilization 37%, errors 0, latency 2.1 ms. So even though your allocation is just numbers, physically it's laser light through glass fiber managed by optical and routing system. That's why it's so fast. So internet backbone. So undersea, this one of the representation of this. You have a submarine cable system here. PH landing station router, fiber, JP router, NTT, physical link, and this is the network part. PHP PLDT core routers, NTT core routers, BGP peering, exchange IP routes. So as you can see, they have BGP in the network side with routers, and then your home network, laptop IP 192, and then your Mac, Wi-Fi L2/L1, and then router, public to private, fiber LAN to PLDT, local node. And then PLD network or router processes packet, reads IP like 157.242, and then forward via BGP toward Japan, and then to submarine cable, and to Japan ISP NTT. Receives packet, routes internally to Facebook data center. So this is how you send message to Japan via messenger. That's why it's fast. And then also, again, it remembers the session, right? So messenger server process your message, sends reply back, same path, reverse. So let's say you're trying to create your own IP. Let's say you have users in Bulacan, local file distribution. Your Bulacan is the data center, your router switches here, the DHCP, IMAP, etc. You basically need to rent this black hole fiber to Manila, like 100 kilometers. Why? I mean, you can create it, but it must be underground because cars could go into it. Now your router in Manila DC, you bring this to their fix or EPLDT, etc. Usually it's near Manila Bay. And then there's a short path cable that will connect that, the fiber that you put there to be able to route the traffic to your customer in Bulacan. So this once you have that, the black hole fiber is easier in the data center because it's just a short path cable connecting their routers. So here PLDT or global router, they're already connected globally, so you don't need to connect it to them because you're just a new ISP. Now they are now the one connecting two undersea cables that will then connect to Japan or US and then to global internet.